Picking up where we left off with calculus with parametric equations, I'd like to describe how to calculate arc length using parametric equations. When we first described what arc length was a few chapters ago, we started off very similarly to how we always start off. Suppose we have y as a function of x, and suppose we want to go from x equals a to x equals b. We want to figure out the exact length of the curve associated with this function. The way that we did so is we said, let's start by chopping this up into a bunch of little tiny subintervals. And on each of those subintervals, we're going to make an assumption about the curve. And the assumption that we're going to make about the curve is that on each of these subintervals, each of these is going to be connected or approximated using a line segment. Any single one of those line segments, if blown up, would look something like this, where we have a nice consistent change in x all the way through. And then we have a bit of a change in y as well. From interval to interval, it was possible that y could change, which is why we would index this using a y sub I. Now if you take the change in y and you take the change in x and you put them all in the same spot at the same time, it creates a right triangle with the change in the arc length. Then we take all of those, we add them up, we allow the number of subintervals to go to infinity, and poof, it's an integral. The important thing that we got out of this, though, is the Pythagorean theorem. And it was through the use of the Pythagorean theorem that we were able to come up with a couple different arc length formulas as far as what it was that we were integrating. In order to actually solve for ds, it was necessary to take the square root of both sides. We wound up with the change in s was equal to the square root of the change in x, quantity squared, plus the change in y, quantity squared. Now, by factoring out either a delta x or a delta y, we were able to come up with two different arc length formulas, one of which being the definite integral from a to b of the square root of 1 plus a derivative squared. In fact, they both take that form, just depending on which kind of derivative you were interested in taking. If you had y as a function of x, you would likely use this one, whereas x as a function of y, the derivative would be flipped and we'd see a dy out here. We would need y values. The way that we can make this work parametrically is by going back to this idea right here that delta s is equal to the square root of delta x squared plus delta y squared. What I'm going to do is factor out a delta t squared from each of these things and say that this would be equal to the change in x over the change in t, quantity squared, and the change in y over the change in t, quantity squared. Factoring out the delta t squared allows us to multiply by a delta t. This moves very nicely into an integral in the following fashion. Arc length is going to be equal to the definite integral from t1 to t2, whatever those t values happen to be, of the derivative of x with respect to t squared plus the derivative of y with respect to t squared dt. Radical ends after the second square. So this formula is what I'm going to be using to approach the following example problem. I'm going to find the exact length of the following parametrically defined curve. We have x equals 7 plus 2t cubed, y is equal to 8 minus 3t squared, and we're going to go from t goes from 0 to 1. So first we'll need a couple derivatives. We'll take the derivative of x with respect to t. 7 goes to 0, 2t cubed would become 6t squared. Additionally, the derivative of y with respect to t, 8 goes to 0, and negative 3t squared goes to negative 6. So next thing we'll do is square each of these and add them together. All that I'm doing is setting up my integrand before I actually evaluate it. So this will be 6t squared plus negative 6t squared. Squaring each of these gives me 36 t to the fourth plus 36 t squared. Now, in anticipation of what I'm about to do, which is take a square root of both of these things, I am going to factor out a common factor. I'm going to factor out the largest perfect square that I can. The largest perfect square that I can factor out would be 36t squared. From 36t to the fourth, that would become t squared, and from 36t squared, that would become plus 1. So the thing that I'm going to be integrating is what I get after I take a square root of all of this. So taking the square root of 36t squared and t squared plus 1. Normally when I take the square root of something squared, I'd have to use an absolute value, but because we're only using non-negative values for t anyway, this will be 6 times t times the square root of t squared plus 1. So using the formula from the previous page, as a quick reminder of what that was this formula right here. We are going to say that the exact arc length is going to be equal to the definite integral from 0 to 1 of this expression, 6t times the square root of t squared plus 1 dt. It is possible to evaluate this through the use of trigonometric substitution, but u substitution will likely look nicer. So if u is equal to t squared plus 1, then du would be equal to 2t times dt. I can borrow a 2t from the 6t, leaving me with 3. Square root of t squared plus 1 remains, and then we'll have a 2t times dt at the end. Just splitting the 6t into a 3 times 2t and separating appropriately. This is where I'll make my substitution. This will become 3 times the square root of u times du. Now additionally, I need to change over my limits of integration. So let's plug in t equals 0. We get 0 squared plus 1, that'll be 1. And let's plug in t equals 1, that'll be 1 squared plus 1, that'll be equal to 2. So limits of integration will go from 1 to 2. Integrating square root of u, we'll consider that as u to the 1/2 power. And we'll have 3 times 2/3 times u raised to the 3/2 power, going from u equals 1 to u equals 2. We can take the 3 and the 3 and cancel those out. We'll be left with 2 times 2 to the 3/2 power minus 1 to the 3/2 power. There's not a whole lot of further simplification that you need to do, but if you wanted to, anything to the 3/2 power would be equal to itself times the square root of itself. So final answer for this one, I would say 4 square roots of 2 minus 2.